Hello, my name is Andrea Wingenroth, and today I'm going to be giving a presentation on the effect of diastolic blood pressure and pulse rate on systolic blood pressure, and we're going to be analyzing this in Minitab. So let's go ahead and get started. So the problem I chose is 4.4 and 4.48, and in these problems, we are given the blood pressure data for an adult male. And our objective is to fit a linear regression model to the given data using systolic blood pressure as the response variable and diastolic blood pressure and pulse rate as the predictor variables. So it is important to understand a bit about the background of our problem so that we know exactly what kind of solutions we're looking for when we're solving the problem. So I went ahead and included these definitions. So we can see that systolic blood pressure is the pressure exerted when the heart beats and blood is ejected into the arteries. And diastolic blood pressure is the pressure in the arteries when the heart rests between beats. And we can see those here. Just for a quick visual to kind of understand our problem and what it's asking us to find a relationship between. And then when you're given a blood pressure at the doctor's, you can see it's systolic over diastolic. So moving on, let's talk about our statistical approach. So we are going to be using a linear regression model, and a linear regression model can be used when two or more variables are related to an outcome. And a multiple linear regression model, as shown here, can be used when there's multiple x values. As you can see, there's x1, x2, you can even have more, but in terms of this problem, we have two values of x. So y is our dependent or repressor variable, and x1 and x2 are our independent variables or our predictor variables. Beta naught is the intercept of the plane, and beta 1 measures the expected change in y per unit change in x1 when x2 is held constant, and the same goes for beta sub 2. Epsilon is our error term, and so let's go ahead and look at the data we're given. We're given this observation row or column, which gives us the date of these observations of blood pressure. So we can see that it spans between a couple months, which isn't that long, but it's not super important for the relationships that we're looking at right now. So then we can see we're given the systolic blood pressure, the diastolic blood pressure, and the pulse rate. And the ranges aren't too big, but so we have about 25, I believe, observations, and we're going to see how exactly diastolic and pulse rate might affect systolic, and we're going to find out using a linear regression model if they are related and if one can predict the outcome. So in our analysis in Minitab, we're going to see which predictor variables are significant, meaning do they have an effect on the response variable, which is systolic blood pressure. All right, so let's look at how Minitab models this regression. So the method of least squares is used to estimate regression coefficients in multiple linear regression models. As I said before, we have 25 observations in this data set, which is enough to see some sort of relationship when we model the regression. So once we observe Minitab outputs, we can come to conclusions about this data. So if we look right here, we can see that Minitab most likely solves using these matrices, where y is an n by 1 matrix of dependent variables. In our case, this is the systolic blood pressure, and x, which is a matrix including all independent variables. For us, that is diastolic blood pressure and pulse rate. And then beta is a matrix of the regression coefficients. And epsilon is a matrix of random errors produced by these predictions. And then we can see up here, this is the least squares estimator of beta, and that is what Minitab uses to produce its outcome and to see if there is a regression for our data set. We are going to use Minitab to see which variables are significant for regression model. And in order to do this, we're going to use a two-sided hypothesis test. So we're going to be answering the question, do the input variables affect the output? Meaning, does diastolic blood pressure and pulse rate affect systolic blood pressure? Our null hypothesis, if our null hypothesis is true, then there is no relationship between the input variables and the outcome. This is our null hypothesis here. And our alternative hypothesis is going to say that there is a relationship present and that the linear regression model is a good fit for our data for at least one J. So at least one independent variable can predict an outcome and it has an effect on the outcome. So let's head over to Minitab and see how we can put our data into Minitab to get a result. Okay, so now once we're in Minitab, we can go ahead and insert all the data from our problem. We're given the observations dates. As you can see, it's within the span of a couple months. And then we're also given the systolic blood pressure, diastolic blood pressure, and the pulse rate. And we can go ahead and create a linear regression model by going to the top panel and choosing stat, regression, fit regression model. In here we see responses, continuous predictors, and categorical predictors. In our responses, this is going to be our Y value, and we're looking for systolic blood pressure to be our response. For continuous predictors, we have two. These are the X values. And we have diastolic blood pressure and pulse rate. So now we can go ahead and look at the settings that we have. Some important settings we might want to look at are graphs. So we can have individual plots of a histogram with residuals, normal probability plot of residuals, residuals versus fit, residuals versus order. And we can also do 4-in-1, which shows us all of these in one big picture. I'm going to choose the individual plots, and I'm going to go ahead and pick normal probability and the residuals. I'm not going to do histogram just because I prefer these three over it. Then we can press OK. Another thing we might want to look at is results. And instead of simple tables, we can have expanded tables. This is just going to give us a bit more information on our relationships. So this looks good to me. Let's have Minitab bring us the results. So as you can see, Minitab puts out the regression equation at the top here. This is the equation which shows how you might estimate the systolic blood pressure. We're also given the 95% confidence interval here with in terms of the constant here, 61.5 diastolic blood pressure and pulse rate. We're gonna go over this once we head back to the slideshow, but we're just gonna summarize here what's going on in Minitab. We're given the R² values and a few other related values, and then we're given the analysis of variance, and you can see an important part right here is the p-value. We can also see our error and somewhat of how this fit is, how the regression fit goes with our given variables. Then you can see this is the plots we chose in the settings, the normal probability plot, the versus fit plot, and the versus order plot. And we can go ahead and analyze this back in PowerPoint. Okay, so let's take a deeper look at what the Minitab outcomes are. And analyze the results. So as you can see here, we have the normal probability plot, and we can see this line of best fit. All of our data points lie pretty close to this line of best fit, and we don't really see a pattern or any major outliers. So we can say that our data is normally distributed along this line. And then if we go ahead and look at the versus fits plot, you can see that we have random distribution of points, and there is really no pattern or trend. We don't see a line, we don't see, clumps of data sets, data points from our set. And this is actually a good thing. We want our residuals to be random. This is a good sign that our regression model fits the data. Then if we look at our versus order plot, we can also see that there is really random distribution. It just is back and forth along this zero axis. And this is also a good sign that our data will fit the model for linear regression. So let's analyze the other outputs, the numerical outputs that Minitab creates. So this is our regression equation. And you can see that 61.5 is our y-intercept. And then we can go ahead and estimate what our systolic blood pressure is going to be with any input of diastolic blood pressure or pulse rate. So this is really the equation you would use to predict the outcome of systolic blood pressure using either one of these. So then we look at the coefficients that Minitab puts out, and we can see that we have, this is one of the more important parts, the 95% confidence interval. And this interval, so for the constant, you can see it's from 23.2 to 99.9. We can see that it is a range of values for which there is a probability of 95% that the true beta is present in this range. As you can see, there's for pulse rate, it's a smaller range, and as well as diastolic blood pressure. And our constant has a big jump in possible beta values. So moving on, we're going to look at the analysis of variance. So some important things to point out are our p-values. So when the p-value is low, our null hypothesis must go. And as you can see, our regression here, the regression is 0, which means that there is in fact, or the regression model in fact does fit our data. If we look at our pulse rate p-value, we have 0.012. This is higher, of course, than 0. However, it's still quite a bit less than 0.05, which is our alpha risk. And we can go ahead and say that this is significant. This is affecting our systolic blood pressure. So pulse rate does in fact have a relationship with systolic blood pressure. And if we look at our diastolic blood pressure, we can see that the p-value is 0 again. This means that there is a relationship between diastolic blood pressure and systolic blood pressure, and it's even more so strong than that of the relationship between pulse rate and our systolic blood pressure. So we can see, because of these p-values, because they are so low and lower than our alpha risk, that there is in fact a linear regression model that fits this data. So if we go ahead and look at our model summary, we can see the standard deviation, S, is about 6.48, 6.49. And then if we look at our R squared, we have 62%. Now R squared, it does seem quite low. However, a large or low R squared does not imply that the model is good or bad. We have to take into account other variables and look at the other outputs we're getting from Minitab. We already saw that the p-values outputted by Minitab shows that the regression model is viable. So we can't just say that because the R-squared value is low, that this is not a good fit. So this R-squared value of 62% means that there's only about 62% reduction in variability of systolic blood pressure based off of our predictor variables. So 62% of the data fits the regression model. Although this is quite low, it is still high enough to say that there is a relationship between the data and the model is still adequate. It's maybe not the best fit, however, it does not mean that there isn't a relationship between the variables. In fact, the p-value that we found in Minitab proves just the opposite. So, in conclusion, we can say that the data set follows a normal distribution and our residual plots conclude that the regression model is in fact a good fit for at least one of the independent variables. But as we can see from our data in Minitab, actually both of the independent variables have an effect, meaning that our diastolic blood pressure and our pulse rate affect the systolic blood pressure. So the low p-values we found for diastolic blood pressure and pulse rate show that the null hypothesis must be rejected. The regression model is a good fit. So we had a low R-squared value, but this does not conclude that the data set is a good match for a linear regression. However, it does not rule out the possibility of regression. So there is some degree of predictability which agrees with the idea of regression for the data set. What is our final conclusion? So both our independent variables, diastolic blood pressure and pulse rate, affect systolic blood pressure as seen in the models on Minitab. According to the relationship we found, increasing diastolic blood pressure or decreasing pulse rate will increase the systolic blood pressure. And we can see that by plugging in any values for systolic blood pressure or pulse rate into the regression equation found through Minitab. So if we have a diastolic blood pressure and pulse rate of 0, the average systolic blood pressure will be 61.5. And you can see that here by this constant. That about concludes our problem, and it is easy to see how Minitab can compute these relationships and how we can analyze a regression model on the data set we're given and see if our independent variables do have an effect on our outcome. And in this case, we do see that. We do see that the diastolic blood pressure and the pulse rate have an effect of our systolic blood pressure. So thank you for listening to my presentation. I hope you enjoyed it, and yeah, thank you.